Welcome back to your favorite intermediate algebra course. Today we're going to talk about introduction to sequences and series. A sequence, here's an example of you have two types of sequences. You got these finite sequences, which means it stops, like that 4, comma 8, comma 12, comma 16, comma 20. So you got this sequence of numbers here in this case. And it stops at 20. An infinite sequence, on the other hand, would be if you kept going, okay? As notated by the dot dot dot. Okay, so that this keeps going on forever in that same pattern. You see how it's going up by 4 each time. A finite series, on the other hand, is where you're adding up. Let's take that same sequence of numbers, but let's add them up. That is a finite series, okay, series, so you're summing them up. Now, an infinite series would be if that summation kept going, okay? So you got finite and infinite sequences, you got finite and you got infinite series as well. Okay, you see the difference there. Now let's take a look here at this green example. Writing terms of sequences. We're going to write the first 4 terms of a sequence, and it's defined by. So they're giving you a formula that defines this. And a sequence, by definition, is a function actually whose domain is a set of consecutive integers. Okay, so when you're doing this, what you want to think about is plugging in. We're going to start with n being 1, and then we'll go to 2, and so on. So that's your domain, 1, 2, 3, 4, and so on. Let me move this down a little bit, okay? So if n is 1, what would the number be first? Question mark. And then if n is 2, what would the number be? Question mark. If n is 3, what would the number be? And finally, if n is 4, what would the number be? And you want to write out the first 4 terms here. Okay, so let's go ahead and do it. So let's let n be 1. Negative 1, our n is 1. So we got negative 1 squared, which is negative 1 times negative 1, which is positive 1. So when n is 1, it spits out 1. So let me erase the little question mark. When n is 1, we got 1. All right, now let's do it for 2. Let's follow this formula. When n is 2, we got negative 1 to the n plus 1. So we got negative 1 to the third. So negative 1 times negative 1 times negative 1, which is obviously negative 1. So we got negative 1 when n is 2. Now, if n is 3, we got negative 1 to the n plus 1. So negative 1 to the fourth. So we got negative 1 times negative 1 times negative 1 times negative 1, which is a positive 1. You could probably see the pattern here. Get a positive 1. Now, if n is 4, what's it going to be? So it'll end up being negative 1 to the fifth once you plug in a 4 for n. So it ends up being a negative 1, because negative 1 times negative 1 times negative 1 times negative 1 times negative 1 is negative 1, okay? So here's our sequence. There's our first 4 numbers of this sequence, and we're going to consider this thing to keep going, okay? Let's do another one here. Let's write the first 6 terms of this sequence, okay? So if you have, again, the first 6 terms, so we'll let n be 1, then we'll let n be 2, 3, 4, 5, 6, and so on. I'll keep going, okay? So f of 1 is 1 times 1 plus 3. So we got 1 times 4, which is 4. So we got 4. Now when n is 2, we got 2 times 2 plus 3. 2 times 5, so we got 10. We got 10 for our second term. When n is 3, 3 times 6, we get, oops, 6, sorry about that, 18. When n is 4, we got 4 times 7. N is 5. We got 40. And finally, when n is 6. 54. Okay, so there's your first 6 terms of that sequence there. Okay, there's our first 6 terms. All right, how about if you're actually taking a sequence, so we got this 1, 4, 9, 16, and so on. We're going to write the next term. So can you see the pattern there? And then we'll actually write the rule for that, or the formula for it. Okay, so if you notice, let me write this down here, 1, 4, 9, 16. If you're looking at this thing, you're like, gosh, it looks like it goes up here by 3, and then it looks like it goes up by 5 here, it goes up by 7. So the next one's got to go up by, and you think to yourself, well, it's got to go up by 9, right? So 16 plus 9. It looks like the next one is going to be 25 is going to be our next term, and then it's going to keep going. So we have the next term. We've recognized the pattern, right? And now what we need to do is, looking at that, is we need to consider, well, if n is 1 for the first number here, actually, let me erase this for a minute. Let's start over with this a little cleaner since we got it. Okay, so we know the next number is 25. Now, think about n being 1 for the first one, right? Let's think about our domain here. And what we're going to do for each of those. What would you have to do to n to get 1? You're like, well, I don't have to do anything to 1 to get 1, right? Now look at the next term. So you're looking at the n equaling 2. All right, what do you have to do to 2 to get 4? And then look at the next term. What do you have to do to the 3 to get 9? What do you have to do to the 4 to get 16, to the 5 to get 25? And you probably started to recognize this pattern here. Let's go back to the first term. N is 1. 1 squared is 1. Take the second term. N is 2. 2 squared, 4. 3 squared, 9. 4 squared, 16. 5 squared, 25, and so on. And so right there, you're recognizing, oh, my rule for this thing would be, you could do it in a few different ways. You could say, oftentimes you'll see authors do it this way, a subscript n is n squared. Oftentimes they'll call this a subscript 1, that's the first term. A subscript 2, second term, third term, fourth term, fifth term, and so on. Okay, so there's the rule. That was the fifth term there, that 25. You know, you could also write it in terms of function notation. You know, you could say f of n is n squared. You could also do that. You know, but you'll probably see this more often, typically here. Okay, so a sub n equals n squared. Let's go ahead and write a rule here for this bottom one. Let me go down a little bit. So -1, 2, -3, 4. What's the next term going to be? And you're like, well, I can see it goes 1, 2, 3, 4, except for the negatives and positives, you know, are changing every other time, right? Like -1, then it's +2, then it's a -3, then it's +4. So the next one's got to be a -5, right? And then we're going to have a 6 and so on, blah, blah, blah. But anyways, we got our next term there. It's -5. Now let's think about the rule. Okay, what do you do to 1 to get -1? Well, you get multiplied by -1. But then what do you do to 2 to get 2? You don't have to do anything. What do you do to 3 to get -3? We get multiplied by -1. So you got to kind of mess around with this thing a little bit, where it's changing from negative to positive. And if you remember, do you remember that very first example we did? Let me go back to it here. Let's see, right here in green. Do you notice how it changed from positive to negative to positive to negative? So you're looking at that g of n rule right there. G of n is -1 to the n plus 1. Okay, that might help us right here. Okay. So how about, let's try it with just the simple -1 to the n. Would that work? Would this work? Let's let it be f of n is -1 to the n. Let's see. Would this work? I say, well, if it's 1, it's negative 1 to the 1. That's negative 1. So far, so good, right? Oops, f of 1. So I plugged in 1. Now let's do the same rule. Let's check that rule for 2. Negative 1 to the 2. Well, that's positive 1. And you're like, well, it did change to positive, but I needed to spit out 2, right? I needed to spit out 2. So what could I do to this formula so that when I plug in 2, it'll spit out 2? So you're like, well, the negative 1 to the n is nice because it does switch it from negative to positive and so on. How about if I do this? N times negative 1 to the n. Is that going to work out? Or oftentimes, actually, let me write it the other way. Negative 1 to the n times n. Okay, so times n down below here. Let's test it. Negative 1 to the 1 times 1. There's a negative 1. There's a 1. You're like, okay, that works. Negative 1. Let's plug in 2 now. F, good grief. F of 2. So we got negative 1 to the n times n. So negative 1 squared is positive 1 times 2. Hey, there it is, 2. Spits out 2. Check mark. Let's try 3 now. So negative 1 to the n times n. Well, negative 1 to the third is negative 1. And that's 3, so we got negative 3. Hey, that works. When I plug in 3, I should get negative 3. How about 4? Negative 1 to the fourth times 4. That's a positive 1 times 4. There's the 4. Plug in 5. It'll spit out negative 5. That's what it is. There's our rule. Of course, the next term in the sequence was negative 5, which we already mentioned. Okay, so kind of tricky. You got to think about those a little bit. Okay. Now you're also going to see some summation notation with these series. Okay, so here's, let's say we have this k equals 1, and that that large sigma there means capital sigma Greek letter. How you say that is you could say from k being 1 up to 3 of 2k plus 2. Okay, and so in this case you're saying, well, let me let k be 1 and let me plug it into 2k plus 2. And the little sigma, that Greek letter, means add them. Okay, so let me add. So k being 1, and I'm going up to, I'm letting k be 3 at the end. So that's my upper limit, and k being 1 is my lower limit. Okay, so now I'm going to say, well, let me let k be 2, and I'm going to plug it into this same formula, 2k plus 2. And then let me let k be 3. So I'm going up to 3, and I'm still plugging it into 2k plus 2. Okay, so I have, let's do the k being 1 at the beginning here. Oh, and 3 is where I stop. Okay, so this is my upper limit. This is like my lower limit kind of deal. All right, so k being 1 up to 3, and I'm plugging it into that formula each time. So let's let k be 1. 2 times 1 plus 2. And then I got a big plus, and then I'm going to plug in 2 for k. And then I get a big plus. I plug 3 in for k. Okay, so 2 times 1 plus 2, there's 4. I got a big plus. 2 times 2 is 4, plus 2 is 6. Got a big plus. 2 times 3 is 6. 6 plus 2, 8. Okay, so we got 4 plus 6 plus 8. Looks like we end up with 18 is the sum of that series. Okay, using that summation notation. Okay. Now let's see if we can go. Let's see if we can go the other way. So if we can write this formula here for 1, 3, 5. So right below this, you're thinking to yourself, well, n being 1, n being 2, n being 3, n being, I'm not sure, but we'll have to think about that for a minute. Okay, what do you do to 1 to get 1? What do you do to get 2 to get 3? 3 to get 5, and so on. Okay, what could your formula be, right? You say, well, the next one is going to be, in fact, let's write the next one up there. 1, 3, 5, it's going to be 7, it's going to be 9, 11, and you keep going up to 51, right? N being 1, N being 2, N being 3, N being 4, N being 5, N being 6, and so on, N being something. Okay, what's your formula here? And you're looking at that, and you're like, well, let me start at the seconds. 2 to 3, 3 to 5, and you're like, gosh, it looks like if I took the N value and multiplied it by 2, let's take the third term, N is 3. 3 times 2 is 6, minus 1 gives you 5. Let's go to the next term, 4. 4 times 2, 8, minus 1, 7. Let's go to the fifth term. 5 times 2, 10, minus 1, 9. There you go. And so soon enough, you can write this, the formula for this. You're like, well, it looks like this formula is going to be 2n minus 1. 2n minus 1. And it works for the very first one, too. If you plug in 1, 2 times 1, 2 minus 1 is 1. Okay? So this last value has got to be, n has got to be 26, because 2 times 26 is 52, minus 1 is 51. Okay, so let's write this summation notation. What would the summation notation be? And you're like, well, this 2n minus 1 is my formula, or 2k minus 1. You know what, let's keep it in terms of, well, we'll keep it in terms of n. Really doesn't matter, n or k, whatever. We're going to start with an n value of 1, and we're going up to an n value of 26, such that when we plug in 26, it'll spit out 51. Okay, there's our summation notation for that. Let's go down here to the red example here. N being 1, N being 2, N being 3, N being 4, N being 5. You probably have recognized this to be 1 over N squared. There's your formula on that, okay? And this thing, you notice that this thing just, it just keeps going, doesn't it? So what you're going to do is to notate, if you're starting at n being 1, your formula is that 1 over n squared. And how far does it go? Well, this thing keeps going, doesn't it? There is no, it's not a finite series, it's an infinite series. So we say from n being 1 to infinity of 1 over n squared. That would be our expression, concise expression for that notation written in red there. Okay. Let's keep going here. Next one. Now here's some formulas that end up being pretty handy for special series. Okay. So the very first one, I being 1 of 1, or my being 1 up to n of 1 is just n. So let's think about that for an example. Let's see if this is really true. So is this true? From I being 1 up to n, let's let n be 4, okay, of 1. And supposedly this should end up being equal 4 because we let n be 4, right? It should be 4. We're checking that, right? So let's write this out. Okay. If I is 1, I'm plugging it into 1 plus, now I is 2, then I is 3, then I is 4, right? And each time I'm plugging it into the formula, which is just 1. There's nothing to plug, there's no i's to plug into here. So 1 plus 1 plus 1 plus 1 is 4. 1 plus 1 plus 1 plus 1, did I say that right? 4 of those. Anyways, so it ends up being 4. So that's true. Okay, so that's a handy little formula. Let's look at the second one here. See if this is of any value. So you got I being 1 up to n of I is supposed to be equal to n times n plus 1 all over 2. So let's think about that for a minute. What does that mean? All right, so let's say we go from I being 1 up to, let's say we go up to 5 of I. Okay, so we're gonna let, according to our summation notation, we let I be 1. We're plugging it into I, right, first. And then I is going to be 2. We're plugging it into I. Then I is 3. Then I is 4. Then I is 5. Okay? And we're plugging it in plugging it into I. Okay, so if I is 1, we got 1. If I is 2, we got 2. 3, 4, 5, and guess what that gives us? 3, 6, 10, 15. 15. This gives us 15. Well, let's check this if this is true. Is this really a shortcut? Well, you know how our n was 5, right? So this is saying I can just, instead of writing it out, okay, because in case like n is like 5,000 or something, you can just plug it into this formula. 5 plus 1 all over 2. 5 times 6 all over 2. 30 over 2, 15. Hey, how about that? So again, why is that useful? Well, if your n's not just 5, if you're not going up to 5, you're going to like 5,000, well, you're obviously going to want to plug that into that formula and just have it kick it out for you. Much easier to do it that way, okay? And then that third same thing, you got the I squared. If it's I squared, you can just follow that formula. You can plug n into that, and it'll spit out your summation for you. Okay, so let's look at this one. I being 1 up to 150 of I. You say, well, my formula is I. Let me go back to my special series. So according to that, if I just got the I, right, if right there, then I can just plug it into n times n plus 1 all over 2. So n times n plus 1 all over 2. So I'm going to plug that in, n plus 1 all over 2, right? Where this, that's my n, okay? So this should spit out 150 times 150 plus 1 all over 2. So 150 times 151 all over 2, and that is, got out here, 11,325, okay? So we use the formula to find the summation. Now you do realize this is what the formula means. I'm just making sure. So I being 1, I being 2, I being 3, I being 4, all the way up to, this is I is what you're plugging into, I being clear up to 150. So you're going 1 plus 2 plus 3 plus 4 plus da da da, clear up to 150. Try adding that up on your calculator. That'll take you a while, but you do end up with 11,325. Okay, so again, you can see the advantage to the formula there. Okay, we're given 3 of those. Make sure you guys bring your questions to class. I'll see you soon.